nucleotide reductase enzyme. Remember the one it synthesizes is a deoxy at position 2' from the ribose nucleotides. That's one we call the ribonucleotide reductase, is inhibited directly by hydroxycarbamide, and we had mentioned that. But we are also noting that the ribonucleotide reductase can also be inhibited indirectly by increasing the level of natural allosteric inhibitors such as deoxy-ATP. This is what we call a negative feedback mechanism. The enzyme adenosine deaminase catalyzes the deamination of adenosine to inosine. Therefore, inhibition of adenosine deaminase enzyme, inhibition of the adenosine deaminase enzyme lead to buildup of the deoxy ATP within the tissues, and therefore have negative inhibition on the ribonucleotide reductase enzyme. And once that happens, it means your drug will not be metabolized, and once it's not metabolized, then of course it will have a better activity. So you're looking at some of these things. So this is the drug, the adenosine. So it forms usually tetrahydrointermediate, and then it goes into inosine. So that is the metabolism we are trying to block. And we are saying we have one of them, pentostatin, is a natural product isolated from streptomyces antibioticas, and is a powerful inhibitor of adenosine deaminase. It acts as a transition site inhibitor. All it's doing, it kind of forms something similar to this. That's why we're calling it. It forms something, it looks like the tetrahydrointermediate. It has structural similarity with the tetrahydrointermediate, and therefore, again, the abnormal cell will be able to take it, or the enzyme within the abnormal cell will be able to take it in place of the normal metabolite, and therefore that blocking the enzyme. So it acts as a transition state inhibitor, mimicking the proposed tetrahedral nature of the adenosine tetrahedral intermediate transition state, which I've just shown you. And pentostatin is a purine analog, which is a 7-membered ring structure, all known as 2' deoxyphomycin. So that drug, just try structural modification on that molecule, gives us a molecule that can be able to block the deaminase. And in blocking the deaminase, of course, as we have said, you will have negative feedback mechanism. Another drug that has been synthesized, which is a deaminase inhibitor, is what we call AHNA, or erythro. Erythro means is specific on the stereochemistry of the molecule, hydroxynonyl adenosine, and this is the molecule. A ribosome moiety is modified by opening the ring up. So again, you can see very similar to adenine, and of course here is where you have your ribose sugar. So the ribose sugar has been opened up, and in that ribose sugar being opened up, then you get that drug, the erythrohydroxynonyl adenosine, which again is an inhibitor of deaminase, and therefore will help us in increasing the nucleotides not being metabolized. And once they are not metabolized, then there will be negative. There will be an increase in those nucleotides. And once there is an increase in those nucleotides, then they will have a negative feedback mechanism on the synthesis of the nucleotides, killing the abnormal cells. And I think that is the last one of the antimetabolites, and quickly move to the other class. And the other class is the antibiotics. Again, we have mentioned antibiotics, and here we are calling them antibiotics because they are naturally occurring compounds that are produced by living microorganisms, and at low concentrations can have activity against other microorganisms. And remember, when we were doing the definition, we said including cancer cells, because cancer cells are also living. Cancerous cells are also living. So that's why we are calling them antibiotics. They are compounds produced by living microorganisms, and at low concentrations, they have good activity against, or they are cytotoxic. They have good activity against cancer cells. So many of the antineoplastic antibiotics are produced by soil fungus, like streptomyces, and this is a microorganism we had mentioned a lot when we were looking at the antibiotics. And some of them include the anthracyclines. This is a class that we look at, which has doxorubicin, daunorubicin, epirubicin. We also have metoxantrone. You see that one is is a derivative, or is a modified. It's a structural modification of anthracyclines when we look at the structure, and of course also idarubicin. So all those, we have 1, 2, 3, 4, 5, but the main anthracyclines are doxorubicin, daunorubicin, epirubicin, and idarubicin. Methoxyntron is an anthracene derivative. So those are the main ones. We look at their structure, and then we have the actinomycins, and under actinomycin we have dactinomycin and plicamycin. We have dactinomycin and plicamycin, and then of course we have miscellaneous within the same, mitomycin, bleomycin. You look at all these antibiotics, look at their structure. There's some of their structures are very complex, so we will mainly highlight the areas that are changeable, the areas where there is structural modification to change one molecule to another, because most of them have very, very complex structures. Others are not very complex, and you look at their structure. The anti-tumor antibiotic drugs have multiple inhibitory effects on cell growth, but primarily act by disrupting DNA function and cell division. So their mechanism of action, again, they have several ways in which they can stop DNA division or DNA replication. They can do so by intercalation. They can do so by alkylation. They can bring about strand breakage either directly or as a result of enzyme inhibition, whereby you have two very important enzymes, the topoisomerase 1 and 2, and also the gyrase. So they can block those enzymes, or they can cause direct breakage of the strand. Remember, again, the DNA, you are replicating the DNA, it must first of all separate into the single strands. Once you break that strand, then of course the replication or transcription will not continue. Topoisomerase enzymes are responsible for the unwinding and relaxation of the DNA so that transcription may occur. Single strand break in DNA caused by cytotoxic free radicals. So this is the last one. This was just a further relation to that. So we can also have single strand break in DNA caused by such toxic free radicals generated from the drug. When the drugs bind the enzyme, you have generation of free radicals or even ions, free radicals or even ions, and those free radicals and on those ions can now again bind the strand and cause it to break. They can bind the strand. Remember, they have excess electrons. They are nucleophilic. They can go for electrophilic portions of the DNA or the strand and cleave it, break it. And when, of course, it breaks, then we'll have a problem with the replication or the transcription. What are the steps in intercalation? There are several steps in intercalation. Of course, you look at these structures and they have such a good structure, a flat structure, where they can just go in between. Remember, when you look at a DNA has two strands, one strand having a base, a sugar, and it has a base, a sugar, and a phosphate. And of course, the other strand also having a base, a sugar, and a phosphate. And the bases are usually in the middle, and the bases are joined to each other through hydrogen bonds. Bases are joined to each other through hydrogen bonds. So when you get an appropriate molecule as a drug, it can come and sit in between. So it comes and separates the two strands, sits in between the two strands, and because it has also groups that can interact with both the strands independently, that molecule interacts with the different strands, and in interacting the different strands, then definitely it fixes those strands and transcription or replication will not happen. And that's what we're calling the intercalation. And the intercalation will happen, as we have said, the shape of the drug is such that it can sit in between the DNA strands, and also that drug has areas or has sites, some areas of electron deficiency, some areas of a lot of electron density, and therefore those areas can allow for interactions, and once the interactions happen, then they will not allow for the DNA to separate or the strands to separate, and ultimately you block the division. And that's what we are saying. So the intercalating drugs contain a planar, and you're going to look, a planar means it's just flat. planar molecule or heterocyclic, either aromatic or heteroaromatic ring system, which can slip into the double helix of the DNA and distort its structure. Drug induces a cavity between the base pairs so that interaction occurs between the drug and the DNA. Just as we have said, it comes in, there's a separation, and it sits there, and the drug now and the DNA strands can have an interaction. The interaction of the intercalator, which is a drug, and the adjacent base pair of the DNA occurs by the overlap. Remember, when we were looking at, I believe, some time place in first year, second year, you looked at the electronic configuration of atoms, and of course we are told we have s orbitals, you have p orbitals, you have d orbitals, you have e, and you have f orbitals, and some of these p, like the p orbitals, are usually not full, and because of the fact that they might contain only one electron, so another electron from another atom can come and form a bond, and that's why we are saying that the p orbitals of the intercalator, which is the interaction of the intercalator drug and the adjacent base pairs of the DNA occurs by the overlap of p orbitals of the intercalator and the base pairs. As I have said, most of the p orbitals usually have one electron, and therefore they can allow for formation of covalent bonds. The p orbitals of the intercalator or intercalation species are provided by a combination of aromatic and conjugated system that impart the planarity required for the intercalation. So we remember this planar, the planar aromatic, heteroaromatic molecules are the same ones which will be able to provide the p orbitals, which can help us in intercalation or interaction between the drug and the bases. The side chains of the intercalator have a cationic moiety, cationic meaning they do have a positive charge. They do have a cationic, which may form an ionic bonds with the anionic phosphate backbone in the DNA. Again, remember, our DNA has a phosphate backbone. It has a phosphate and a sugar backbone. That phosphate has a negative charge. So if the drug has a cationic site, ionic bonds also will be formed. The overall result of these interactions is to cause a local bend or a sharp twist or curve or cut in DNA results in a local shape distortion. So this drug comes in, there is a distortion in the DNA, and indeed, once there is a distortion in the DNA, because this molecule has sat in, then the normal separation of the double helix will not happen. You can also have because of that intercalation, you can also have inhibition of topoisomerase enzyme or the DNA gyres. And once you inhibit those enzymes, again, remember, they are very, very important in the replication. And the first class, so that was just the general, just describing generally how the intercalation occurs. And that's because the intercalation is just sitting in between the two strands, and therefore preventing them from undergoing replication. We have the first class, the anthracyclines and anthracene diones. And the anthracycline antineoplastics, again, are naturally occurring. They are from the streptomyces microorganisms. Anthracycline antibiotics are very closely related to the tetracycline antibiotics. We have looked at the tetracycline. These are also called anthracycline. The structure might be different, but they have some similarity. They have four rings, but of course, they will have structural differences, but also some structural similarities. Structurally, they are glycosides and contain an unusual sugar portion, again known as L-dinosamine. When we were looking at the macrolides, we did mention about unusual sugars, and these are an amino. This is an amino sugar portion, and this is an amino sugar, and then a non-sugar organic portion. So we have a non-sugar organic portion, that's a portion which does not have sugar. And of course, they have this dinosamine. And of course, the dinosamine, being an amino sugar, it is bringing in a basic moiety. And of course, that basic moiety can undergo protonation, giving us what we call a cationic site. In anthracyclines, their glycone moiety is specifically called the anthracyclinone or anthraquinone. Of course, their glycone is that portion that does not have the sugar. So we call it anthracyclinone or anthraquinone. And when we look at the structure, it will be very clear. How do they intercalate? So before even we go there, let us look at their structures so that we can understand. So these are the anthracyclines. So you can see why we are saying they are very similar. You can see that structure, very similar and of course different from the tetracycline. So you can see they have that aromatic ring, they have the quinone ring, hydroxyquinone ring, and then of course they have that other ring. So the anthracyclines, and you can see that their structural differences can be in this portion of the sugar, whereby R4 can either be a hydrogen or it can be a hydroxyl group. Therefore, R3 can also be a hydrogen or hydroxyl group. In other words, there can be epimerization at that point, and that's why we have the epirubicin. Epi means it is the epimer of doxorubicin. Epirubicin is the epimer of doxorubicin, again giving structural difference and of course differences in the activity. Therefore, that area can change, and that, as I have said, it's either hydrogen or hydroxyl group. You can also have, that's R4, R3. You can also have a change in R1, and R1 is here, whereby it can either be a hydrogen or it can be a methoxy group. It is a hydrogen in idarubicin. It is a methoxy group in all the others, doxorubicin, daunorubicin, and epirubicin. And then the other place that can change is this place here. It can either be a hydrogen to give us a methyl group, as in idarubicin and daunorubicin, or it can be a hydroxyl group to give us hydroxy methyl group, or a primary alcohol, as we can see is found again in epi. That is the two, sorry, the two is found in doxorubicin and epirubicin. So in daunorubicin, R2 is a hydrogen. In idarubicin, it is a hydrogen. In both doxorubicin and epimers of each other. So the only difference is in their position R3. So the daunorubicin, idarubicin, they have a methyl group there, whereas doxorubicin, epirubicin have an hydroxymethyl group. So those are the main anthracyclines. So anthracyclines, so how do they undergo intercalation? The anthracyclinone, that portion of the structure is large. This is a area we call the aglycone, the area without the sugar. It is a large and predominantly aromatic, therefore flat. This flat ring system slides between the two DNA strands, orienting itself in a perpendicular fashion relative to the long axis of the. All we need to understand at this point, we are saying it is an aromatic flat portion. It fits itself. It intercalates between the DNA. So it sits intercalates between the two DNA strands, and therefore not allowing this molecule to separate. Once intercalated, the anthracycline DNA complex is stabilized through van der Waals forces, hydrophobic and hydrogen bonds. This will happen because these molecules will allow, they have those areas, they will allow for van der Waals forces. Remember, van der Waals forces or the London forces happen because of differences in distribution. There is differences in distribution of the electrons within the atoms, and therefore at a particular days they are actually induced. You have induced bonds or induced forces. So within the atom, you will find as the electrons go around, the orbitals go around the nucleus, those electrons at one time can be more concentrated in one area of the atom, and the area where they are concentrated will have a delta negative charge. The area where they are not concentrated will have a delta positive charge. So that area where they are concentrated with a delta negative charge can interact with another molecule where there is less concentration, and those are the ones we call van der Waals forces. So they happen in all molecules as long as the electrons, of course, are going around the orbital. The electrons are going around in the orbitals or going around the nucleus. So there can be van der Waals hydrophobic areas, like we have talked about the benzene. The benzene is basically lipophilic, and therefore it can interact with another molecule which is highly lipophilic, and hydrogen bonds. Hydrogen bonds, whenever you have nitrogen and oxygen in molecules, and of course hydrogens, then you have the possibility of having hydrogen bonds. Binding is best in DNA regions that are rich in guanine, and also cytosine bases. Remember, guanine has a hydroxyl group at position 6, and it has an amino group at position number 3. Cytosine also, cytosine the same. Cytosine has also an amino group and a keto group. The protonated 3' amino group on the daunosamine. I remember I say the daunosamine has an amino group, so it will be protonated at physiological pH. Also stabilizes the intercalated complex through intercalation with the anomic DNA phosphate, which we have already mentioned, or formation. It can also form covalent bonds with the carbon 2 amino group of guanine. And therefore, when that happens, these bonds that are being formed between this strange molecule, between this drug and the DNA, are stabilizing this molecule. And once that molecule is stable, then that it means the drug will be firmly held. And once the drug is firmly held, it will prevent the separation, or it will prevent the separation of the strands. And once you do not have separation of the strands, application will definitely not happen. So this is just a structure to show us the structure. So there, of course, doxorubicin, we did say it has a methoxy group there, and there's a methoxy group at that point. And then here, of course, it's where it's joining at this position. That position. This is our position. This can count from position 1, position 2, position 3, position 4 there. So here it has the alpha hydroxyl group and the reverse one. And of course, also daunorubicin has the same. It's epirubicin, where this one you look up. So the reverse one, this group you look up. So the carbon 9 acetyl group, daunorubicin. So we are only saying, if you look at doxorubicin, it has a hydroxy acetyl group. It has a hydroxy acetyl group. When you look at daunorubicin, it has an acetyl group. And of course, they have a methoxy group at that position. And of course, the hydroxyl, the hydrogen hydroxyl arrangement is, of course, the same. So the difference is only at, as we can see, at position 9. Difference, at position 9, instead of the hydroxyacetyl group, we have the acetyl group. We have the acetyl group. Then you have the epirubicin, again, just showing the structure. Again, it has the methoxy group here. Now you can see the change in orientation here. This was looking down. That was looking down before. It's position 1, position 2, position 3, position 4. So at position 4, this was looking down in daunorubicin, in doxorubicin. Now it is the epimer, and that makes a difference. In idarubicin, the sugar, there is no epimerization. So the position 4 hydroxyl group is just the same orientation as in doxorubicin and daunorubicin. The difference is at position number 4, that at position number 4, in place of a methoxy, you have a hydrogen. That is the main difference. In place of the methoxy, you have a hydrogen in that position. The second generation and the cyclic idarubicin, because of that, definitely it has much higher lipid solubility than the others, lacks a methoxy group at carbon 4, so it is less polar and has an altered metabolism which prolongs its half-life. Because of lack of the methoxy group, it has higher lipid solubility and much longer duration of action. Then we also have another drug we call valrubicin. And if you look at valrubicin, you can see several changes there. It's position 1, position 2, position 3, position 4. Position 4 still carries the normal hydroxyl group. That position 4 is okay. But if you look at this position group here, the group here, the hydroxyl group at that position there, that is position 3, has been replaced by a different substituent there, which is an amino acyl trifluoro derivative. So that is completely different there. If you look at also this position here, is also very different. There is a different substituent at that position and a different substituent at that position, and that is what makes a difference in that drug. The methoxy group there is the same sterile solution, and this drug is used for what we call intravesical instillation. We mainly use it in the bladder. It is intended for intravesical administration in the urinary bladder. It is applied as a non-aqueous solution that should be diluted before intravesical administration. So you can see non-aqueous, meaning if it's non-aqueous, means the diluent does not have any water. It is usually formulated at a concentration of 40 milligrams per ml in 50 polyoxycastor oil, 50 dehydrated alcohol. So you can see 50% dehydrated alcohol, 50% polyoxycastor oil. So it is an oily preparation without preservatives or other additives. The solution is sterile and non-pyrogenic. So we are saying, of course, when the oily preparations are usually very painful to inject. But you can see it is intravesical, and means you inject it directly into the bladder. And once you do that, of course, also you minimize toxicity. So that is also valrubicin, and therefore we have quite a number of about 4 drugs there, whereby there is very slight structural modification with retention of activity. SAR, the anthraquinone, chromophore, sphingosine, and the hydroquinone moiety on adjacent ring is an important structural feature of the anthracycline. So we are saying, you can see we are numbered the same way as we number anthracycline A, B, C. So what we are saying is that ring B and C are important for activity. That is the quinoline and the hydroxyquinoline ring. Both of them are important for activity. So the quinone and hydroquinone moiety on adjacent ring are necessary for activity of the anthracycline. Remember, this must be a flat molecule. The phenolic hydroxyl group present in this core undergo acylation and alkylation under standard reaction conditions. So we are saying O methylation. So we are saying that the phenolic hydroxyl groups present in this core undergo acylation and alkylation. They can undergo acylation and alkylation under standard reaction conditions. O methylation of carbon 6 or carbon 11 phenolic groups results in analogs with markedly reduced activity. Let us look at position 6 and position 11. Position 6. So this is position 6 and position 11. It is still highlighting what we have said, that this position 6 and position number 11 we require this fixed group here, the quinone and the hydroquinone. So any changes, so we are saying if you change that hydroxyl group either at position 6 or position 11, you will decrease the activity. So that analogs with markedly reduced activity. That further stresses the point number 1. Carbon 4 modifications such as demethylation and deoxygenation do not affect bioactivity. In other words, we are saying position 4 is this one. You can have hydrogen, means you can also have a hydroxyl group, you can have a methoxy group. That does not influence biological activity, but it can influence the pharmacokinetics. The drugs used to be have anti-cancer activity, but as we have seen in idarubicin, it can influence the pharmacokinetics in that the drug may have higher bioavailability depending on the group that you have there. The transformation of carbon 5 carbonyl to the corresponding immuno functionality results in an analog that retained activity and was found to be significantly less cardiotoxic. You will note that one of the major problems with these drugs is cardiotoxicity. So we are looking at position number 5. This carbonyl group can be changed with an immuno group with retention of activity and decrease of cardiotoxicity. So that's our position number 5. Ring A is an alicyclic moiety having a 2-carbon side chain group and a tertiary hydroxyl group at carbon 9. If you look at ring A, it has this group here, and it also has that group there. So it does have a hydroxyl group there. This is a tertiary hydroxyl group there, and it also has this group here. This group can either be an acetyl group, or it can be an acetyl group, or it can be a hydroxyacetyl group with retention of activity. So it's position 9. Let's see, where is it? Yeah, there is also this one here. It has a hydroxyl group there. Let's see, go back. So they have a tertiary hydroxyl group at position 9, and they have also the acetyl derivative, and the hydroxyl group at position number 7 has been attached to the down-rubicin or the amino sugar. You can see this is why we are calling it amino sugar, because of this. We are calling it amino sugar because of that amino group. That's why it's down-rubicin and amino sugar. So we are saying, if you look at position number 9, it has 2 substituent. It can have the acetyl group, which is this one, and of course a hydroxyl group. This acetyl group, this CH3, can be CH2OH, and of course still with retention of activity. So there is that hydroxyl group and that acetyl or its derivative, and there's another hydroxyl group at position number 7 that has been derivatized, or that has been joined or derivatized through a glycosidic bond and joined to amino sugar, which we are calling down-rubicin. 2-carbon side chain, acetyl or hydroxyacetyl, tertiary hydroxyl group at carbon 9, which we have looked at. Now, it also has a hydroxyl group at the chirocarbon number 7, which we have also looked at, and a dounosamine amino sugar residue attached to the carbon 7 hydroxyl group through a glycosidic linkage. I think all that is obvious. You can be able to see it. So we are saying this is the anthraquinone or anthracindione. So if you look at this is 3 rings, whereas the anthracene and the cycling derivatives have 4 rings. So the other drug that we are going to look at has the synthetic derivative has 3 rings, anthracindione, because of that, and it is not an anthracycline, it is an anthracindione or anthracene derivative. And that drug is the one we called metoxantrone. Metoxantrone has structural similarity with the anthracyclines, but with a difference in that it has 3 planar rings, all joined, all fused to each other, as opposed to the anthracyclines, which has 4 rings. So you can see that ring there. And as we have discussed, you can still see what we have said of that ring and that ring are still maintained. You have the quinone and the hydroquinone ring, and those rings are still maintained. And of course, the third ring, again, which gives that molecule a planar, rigid structure for the purposes of intercalation or going in between the two, or going in between the bases. The metoxantrone, which is the drug I've just shown you, its structure resembles that of the anthracyclines. It's a simplified synthetic analog, where the tetracycline link system has been modified to a planar tricyclic system, which is, again, as we have said, required for the intercalation. If you look at it, it doesn't have any sugar moiety, and that's an advantage, because the sugar moiety is said to be also responsible for some of the cardiac toxicity. The pharmacophore group includes the hydroxyl, oxo, and amino groups, which are responsible for binding with the DNA base pair. So you have the hydroxyl, oxo. Again, if you look at that compound, it has the hydroxyl, the oxo, the amino groups. Remember, for purposes, for intercalation, you have to have those bonds. This amino group here can be protonated at physiological pH. Not so easy for that one because it is adjacent the aromatic ring, but this can be protonated to give us a cationic site, again, which can interact with the bases through ionic bonds. And of course, we did mention that group there is necessary for activity. So the structure may be different, 3 rings instead of 4 rings, but still having groups that can favorably interact with the DNA. Again, the same thing, binds to DNA to produce thread breakage, inhibits DNA and RNA synthesis, and it is used to treat pediatric and adult acute myelogenous leukemia, non-Hodgkin's lymphomas, and breast cancer. It still causes cardiac toxicity, and that is a major side effect of these drugs. So if you look at mentioned doxorubicin, again, we have mentioned its intercalation, just re-emphasizing the same. It intercalates between adjacent nucleotides along the DNA, forming tight DNA drug interaction. This interaction disrupts DNA synthesis and transcription. It can also bring about enzyme inhibition, both of the topisorom 2 and even the DNA gyrase. And once that happens, it will block DNA synthesis. It can also bring strand breakage, as we had already discussed, by generating free radicals. It can generate oxygen-free radicals, oxygen-free ions, and oxygen-free radicals like the superoxide, and this will damage the DNA, again, causing cleavage or breakage, and therefore preventing DNA synthesis. And the same will happen with this, even the other anthracycline derivatives. And though we are giving an example here, we have our doxorubicin here, and we are having the enzyme, the cytochrome P450 reductase, where the oxygen is oxidized and the doxorubicin is reduced. The quinone is reduced to the hydroquinone, and the oxygen is oxidized to the superoxide radical or ion, and that superoxide radical or ion is the one that causes this to break. You can just see they break, and once they break, the continuity of the replication is stopped. Tissues, so that is just to elaborate on the mechanism of action of these drugs. Then you find that if you have tissues with some ample of the enzymes superoxide dismutase or glutathione peroxidase activity, have lower cardiac toxicity, because the superoxide dismutase and glutathione peroxidase are able to reduce the concentration of the superoxide ion. And once they are able to reduce the concentration of the superoxide ion, then you find that there is reduced cardiotoxicity. So tissues with ample superoxide dismutase and glutathione peroxidase activity are protected from cardiotoxicity or cardiotoxicity. And you find that the cardiac tissue lacks superoxide dismutase and the catalase enzyme, the peroxidase enzyme. This may be the reason for the cardiotoxicity of the anthracycline. So we're finding these enzymes help to metabolize or to get rid, to further metabolize the superoxide to savor molecules, and therefore protect the tissues where they are found from cardiac toxicity. Unfortunately, the cardiac tissue does not have those enzymes, and no wonder it's one of the organs that has a lot brings about a lot of toxicity. That is, you can have a lot of cardiac toxicity because of lack of those enzymes. Uses of anthracyclines, doxorubicin. Again, I believe you've done a lot of this in your pharmacology to treat broad spectrum of solid tumors as well as acute leukemias, lymphomas, and childhood tumors. It is indicated for, that is daunorubicin for acute leukemias. Epirubicin is considered effective against breast cancer. Idarubicin is used in treatment of hematological malignancies and can be given orally. Both epirubicin and idarubicin are second-generation anthracyclines with less cardiac toxicity than doxorubicin and daunorubicin. Metoxantrone is used for the treatment of certain leukemias and lymphomas and for advanced breast cancers. You must have done a lot of that in your pharmacology. But we are saying this is a class of drugs naturally occurring with, of course, a bit of structural modification to give us a metoxantrone, but naturally occurring drugs that have been used in the management of cancer, but of course not to forget that of course they will be responsible for quite a number of toxicity, including cardiotoxicity. They will also interfere with the heart muscles, the sugar residue and free radical formation, some of the cause for the cardiovascular toxicity. the sugar radical and the free radical formation. That's why we said when you have the dismutase, which can get rid of the free radical, then you have decreased in toxicity, leads to formation of congestive heart failure, often even years after treatment. You can counteract the effects of this drug with dextrosozone. You can counteract the effect with that drug. And then, of course, also you can give these drugs as liposomes that can be useful as carriers to deliver doxorubicin to target tumors, and this approach is associated with less cardiac toxicity. I believe in pharmaceutics, you have talked about liposomes, where you can formulate the drug, you deliver the drug to the organ, target delivery. And of course, once you have target delivery, then you will minimize the cardiac toxicity. Extravasation injury produces extensive local necrosis. Extravasation is where these drugs leak. They leak through the blood vessels, and once they leak through, they will cause tissue necrosis, or they will cause necrosis around the vein, and that's what we call extravasation. And that also is a big problem. It's a big problem. So you can see this patient, the cancer is eating them up. So most of them are very weak. The drugs also are a major problem in terms of toxicity. And that is why management of cancer, the drugs are expensive, the drugs are highly toxic, and we can understand the toxicity of these drugs because there will not be much selectivity. In fact, the selectivity we use is that the fact that some of these tumor cells produce some of the enzymes in high concentrations, but some of those enzymes sometimes are also produced by the normal cells. So they produce some of the enzymes in high concentrations. So you target those enzymes. But normally there is not good selectivity because the tumor cells and the normal cells are very similar. So those are the anthracyclines. And we can move on to the next class, which is the dactynomycin. It's another drug, or the actinomycin D. Again, it's naturally occurring, and it's a chromopeptide. In other words, when you look at the structure, we will see it has a peptide, and the peptide is important as part of the chromophore. That's why we're saying it's a chromopeptide, and the chromophoric part is substituted 3-phenoxazone 1,9-decarboxylic acid, known as actinosine. Okay, I think when we get there, it's important for us to look at the structure. So we are looking at, this is dactynomycin. So you can see it has two sections. It has the peptide section where you have 1, 2, 3, 4, 5 amino acids and repeated on both sides. And then it has the phenoxazone ring. Again, you can see what we had seen with the anthracyclines. A rigid structure, a flat rigid structure, which is a combination of aromatic and heterocyclic structure required to go and intercalate, fit in between the DNA strands. And of course, you can see, of course, that amino group might not be very, very good, but within the amino acids, you do have amino group, which can be protons at a physiological pH, again, giving us cations which can interact, again, as we have said earlier. Within the amino acids, we also have oxygens, we have nitrogens, again, which can allow for formation of hydrogen bonds. We have hydrophobic areas, which can allow for formation of hydrophobic bonds. And therefore, all those that we have discussed in terms of interaction for the anthracyclines will be the same for this drug. It's only that it has a different structure. It has different groups that are doing similar interactions with what we found in the anthracyclines. So we have the peptides, and you can see we have the different amino acids there. And of course, you can see they bind to give us an lactone there. And then at position number 9, that's why you're saying there is a carbonyl group, carbon 1,9, there is a carbonyl group there, and at that position, there is a carbonyl group, and you have the phenoxazone ring and the peptide ring, which are important for activity. So we are saying the penta, no, yeah. So we are saying there is 1,9 decarboxylic acid. You see, you looked at the position 1, there was a carbonyl group. For the peptide to come in, it must have been a carboxylic group. So there is 1,9. So that's why we are calling it part. Is substituted 3-phenoxazone 1,9 dicarboxylic acid. And so at those two, position 1 and 9, initially there was a carboxylic acid, which has formed a peptide bond with, of course, the amino acids. The phenoxazone, of course, is also a chromophore. It is required. We said you have to have the rigid aromatic area needed for interconnection. It has a dipeptide portion. We have seen that, which is also important. The pentapeptides are namely L-threonine, D-valine, L-chlorine, sarcosine, and L-methylvaline. And even the orientation, the stereochemistry of these amino acids is important for this molecule. Of course, again, to acquire the shape we want, the size we want, for it to be able to properly intercalate and fit in between the DNA bases. We are saying that also the L-methylvaline forms a lactone. We have shown you the lactone by the side chain hydroxyl group of L-threonine and the carboxyl group of L-methylvaline. Again, remember, all these amino acids will have an amino group and a carboxyl group. And those amino groups and carboxyl groups are the ones that come together to form the peptide bond for them to come in. But we are saying also there's this lactone which is formed via the side chain hydroxyl group of L-threonine. Remember, L-threonine has a hydroxyl group on the side, and that L-hydroxyl group and the carboxyl group of L-methylvaline are the ones that will come together. Instead of the amino group coming together with the carboxyl group, now the hydroxyl group of methionine comes together with the hydroxyl group of L-threonine comes together with that of L-methylvaline to give us the lactone. Just a minute, sorry, I forgot to put on my phone. Hello? So again, that lactone is important. We are saying it's formed between the threonine and, of course, also the L-methionine in place of the amino group interacting or forming a peptide bond with the carboxyl group. The hydroxyl group of L-methionine interacts with the methylvaline to give you the lactone. And you can see that is on both portions of the molecule, both position 1 and position 9. An amide linkage is present between the amino group of L-threonine and the carbonyls of 1 and 9. And you can see that there is that carbonyl group. So that carbonyl group is present everywhere. This carbonyl group. Remember, where is this one? Hello? Yes. Hello? 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 Sorry. Hello? 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 Yes. Yeah. Eh. 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 Niko kwa class, wacha nimalize na class kwanza. Niko kwa class, wacha nimalize kwanza. Sorry about that interference. The person insisted, and when somebody insists, never know. We had done that. I went too far back. So we were looking at the structures, and we did say you do have we were looking, an amide linkage is present between amino. You always have amide linkages when you have the amino group coming together with the carbonyl group. You will have an amide linkage between the L309 and carbonyls of 1,9. So the phenoxazone has carboxylic acids, and because it has carboxylic acid, the amino group which is fast coming in will definitely form an amide bond. That's all we are saying at that point. The structural feature of dactynomycin is important for its mechanism of cytotoxicity. The planner, again, this we have mentioned, which facilitates intercalation. The peptide loops are located within the minor groove and provide for additional interactions. Remember, there will be hydrogen bonds, there will be hydrophobic bonds, there will be ionic bonds, all those as we had already discussed. Dactynomycin binds non-covalently to double-stranded DNA by partial intercalation between adjacent guanine cytosine bases, resulting in inhibition of the DNA. Again, the same thing. It will also form covalent bonds again between guanine and cytosine. Guanine, cytosine are the bases that pair up. So it will come in, it will form covalent bonds, it will form ionic, and all those bonds that will help in its being fitted very tightly. And once it's fitted tightly, then of course it will stop the replication of the DNA. Additional hydrophobic interactions and hydrogen bonds are formed between the peptide loops, the same thing we have said, and sugars and base pairs within the minor groove. So that's what obviously that the molecules that we have within these drugs will allow for hydrophobic bonds, they will allow for hydrogen bonds, they will allow for ionic bonds, they will allow for van der Waals forces, and all we require all those forces for is to bind this drug, to hold this drug firmly in between the bases of the different strands so that it will stop the intercalation. That's what we are looking at. So we are saying between here, it's only that we have not put everything. There will be an amide bond here. There will be an amide, there will be L309 and the group NH and then C double bond O. And of course, the same applies to the other side. So that's a molecule that we have for the dactynomycin or actinomycin D necessary for activity. Let us look at the structure-activity relationship. And we are saying the lactone ring in the dactynomycin stabilizes the peptide chains in such a conformation which enables the formation of 4x hydrogen bonds between the phosphodiester oxygen and the peptide. So we are saying the lactone ring is the lactone ring which is formed within the peptide. Again, it stabilizes the peptide chains in such a formation which enables the formation of 4x hydrogen bonds between the phosphodiester oxygens and the peptide and NH. The phosphodiester bond holds the phosphate group to the sugar in the DNA. You see, like where you have the sugar, where you have the DNA. Remember, the DNA has a base, which is the base. You start with the base. The base is joined to the sugar, and the sugar has a phosphate. And under normal circumstances, the phosphate and the sugar join together or bound together through what we are calling a phosphodiester bond. It holds a phosphate group to the sugar in the DNA. So that's the same type of bond. So we are saying that the lactone rings in the dactynomycin stabilizes the peptide chain in such a conformation which enables the formation of 4 extra hydrogen bonds between the phosphodiester oxygen. The phosphodiester oxygen is that oxygen which is in that bond, which is between the sugar and the ribose. So all we are trying to say is that this structure, even that lactone, and that's why we say it's necessary for activity, it helps again to fix this molecule. It increases the interaction again between the drug and, because you see, remember that oxygen lactone is within the drug. So we are saying it is interacting with the bond, or it is interacting with the sugar, and also it is interacting with the phosphate. And in being able to interact, again, all it is doing is fixing, it's making that interaction between the drug and the bases very strong. Amino acid composition contributes to the biological activity of the dactylomycin, so we require the amino acids, replacement of both the proline residues with anything. So you find that those amino acids that are found or that have kind of been put within the dactylomycin are just what is necessary for maximum activity. If you replace them, like you can see, this is what we call pipecolic acid. Pipecolic acid is where you have that 6-membered ring. Prorine is where you have that 5-membered ring. I just give it for an example. So you'd expect that this would fit this, or this, you can exchange this with that. This, you exchange this, you put this in place of that and have good activity. But it has been found that the amino acids as they are, the chlorine, the methyl valine, the threonine, and so on, sarcosin, all of them are necessary for maximum activity. And if you change those amino acids, if you change the amino acids, then you will have decrease in activity. If you remove the lactone bond, and the lactone we said is formed between the hydroxyl group of methionine and methylvaline, if again you remove the lactone, you interfere with the bonding and therefore you reduce activity. So in other words, dactylomycin is supposed to remain as it is for maximum activity. That molecule should not be changed. Change of that molecule will result in reduction in biological activity. What is it used for? Rhabdomyosarcoma, which is soft tissue and even skeletal muscle and hollow organs cancer. Hollow organs is like the bladder and the uterus. You can use it for Wilms tumor. You can do all these things. I believe you have done them in pharmacology. It has life-saving. It's life-saving for women with chromosarcoma resistant to methotrexate, in combination with vincristine and cyclophosphamide in solid tumors in children, and birth effects, bone marrow depression, alopecia, and erythema. Of course, these again are major toxicity of these drugs, and we need them when you have the cancers, but they can also be disastrous. They really cause poor. They really decrease the quality of life in the person. But for some people, of course, when they withstand the treatment, the chemotherapy, there are people who have been cured. Because cured, quote, because sometimes you get kind of cure for a number of years and you find that the remission and of course and so on and so forth. But there are some people who have had early detection of cancer, very early detection, and it is properly treated. Chemotherapy, sometimes surgery, chemotherapy, and so on, radiotherapy, all of them mixed together, if the body can withstand all of them. And you find there are people whereby the cancer has been cured and they have lived a normal life like every other person. But it is indeed a very difficult, very challenging disease. So we have looked at dactylomycin. Another of the antibiotics is bleomycin, and it is isolated again from streptomyces, mixture of closely related compounds where you have bleomycin A, A2, and B2, which are available in nature as blue copper chelates, so they are chelated to copper, A2 and B2. Mode of action, I think I also have their structure. So of course, as I said, some of them are very complex, and you can see how complex this molecule is. It has so many other portions: pyrimidine ring, a primary amide, midazoline ring. And of course, we are saying this molecule, the way it's complex, it is providing again centers which can intercalate, which can bond with the DNA in different ways. It will be able to provide for hydrogen bonds, provide for van der Waals forces, and so those bonds that we were able to mention. But you can see this portion, so we can put the whole of that up there. Perhaps can even put it, sorry. You can put it up to there. You can put this as R. Put up to there as R, and then you can see this section again. This section, especially the bithiazole ring, is very important because it helps in the interconnection. So you have that amide, the ethyl group, but this portion is very, very important. This is a very important portion, the bithiazole region, because it helps in the interconnecting of this molecule between between the bases. You can see how complex that molecule is, but necessary to help us in binding between or intercalating between the bases. So they're saying it's a mixture of closely related compounds, A2 and A2 and B2. The cytotoxic property of bleomycin is due to the fragmentation of the DNA. So the way we said earlier, again, most of the fragmentation that we had discussed occurs by production of radicals, or ions, radicals and ions with cleave. And that in this case happens, it appears to cause scission of the DNA by interacting with the oxygen and the iron 2 plus. And once it binds that, it generates the free radicals which break the DNA. It binds with DNA through its amino-terminal peptide, and the activated complex generates free radicals that cause DNA breaking. The bithiazole ring system intercalates within the DNA. So that helps intercalate between the DNA. And then this drug, DNA, the drug, and the iron. So you can see you have the DNA. So it's a ternary combination where you have 1, 2, 3. You have the DNA, you have the bleomycin, and you have the iron. And that gives you, binds to give you DNA, bleomycin, and of course the iron has been oxidized. And when that happens, this combination, the ternary combination, the DNA, bleomycin, iron 3 plus, generate superoxide and hydroxyl radicals. So generate for you superoxide and hydroxyl radicals. And when that happens again, as we saw with the others, there is cleavage of the DNA. And of course, that stops the synthesis of the replication of the DNA. So we have superoxide and hydroxyl radical production.